Hi everyone. It's mentioned by Das here, I am Indu from India. First of all, I would like to thank the organizers of 15th Helionic Astronomical Conference for giving me this opportunity to present my work. I will be talking about jets, disk wind, and oscillation around Kerr black hole. This is done with collaboration of Bhargav Vaidya from IIT Indore, India, and Christian Fan from NPI, Germany. This results has been recently published in this article. If for more detail, please visit the article. Astronomers and astrophysicists has done many breathtaking observation and theoretical development in the last few decades, but still there are huge discrepancies in the theoretical prediction and the observational finding, especially in the perspective of astrophysical jets. Particularly, the theoretical understanding of many aspects of jets are still unknown, or some are not studied well. We do not know yet how the jet or the wind launch from the black hole or the accretion disk, how they collimate and accelerate to a speed comparable to the speed of light, or how they shine, etc., etc. In this talk, I will be mostly focused on the launching problem of jet. There are two primary mechanisms that can power a jet. That is Blandford-Janiak mechanism, that where the jet is powered by the rotation of the black hole, and the Blandford-Payne mechanism, where the jet is powered by the rotation of the accretion disk, or popularly this mechanism is known as magnetocentrifugal acceleration. In this study, I would like to understand them in detail. From last 2 decades, GRMHD become essential to study, understand the physics around black hole. Many studies have done with GRMHD to understand astrophysical jets around black hole. Most of the studies start with hydrostatic torus in equilibrium as initial condition, and that gives extraordinary detail of physics going around the event horizon, and so the launching of Blandford-Janiak jet. The plot of jet radius versus distance of the jet from the central black hole not only suggests that this is done for M87, that the jet is parabolic and become conical after the boundary radius, and it also suggests that the jet launching radius for M87 is around 5.5 Schwarzschild radius. And it hints that the Blandford-Janiak mechanism is probably responsible for the jet launching in M87. However, similar study in Cygnus A suggests that the jet launching radius for Cygnus A is around 227 Schwarzschild radius. And therefore, at least a part of the jet must be launched, or probably launched, due to the Blandford-Payne mechanism in Cygnus A. And in order to study such scenario, GRMHD simulation with hydrostatic thin disk in equilibrium become very important. There are very few such studies in literature. Kian and Variolis, they studied such disk going from thin accretion disks recently, and they use Spagnansky-Vita potential and non-relativistic particle equilibrium to set up their initial disk. We set up a steady thin accretion disk in hydrostatic equilibrium as initial condition following Novikov and Thorne model. The initial density profile and gas profile is shown in this two panel, panel A and panel B. And we found that the aspect ratio, that is the h by r, that is this height by the radius, the maximum value of aspect ratio is 0.07 for our setup. And we have seen that throughout our simulation, the disks remain thin except very close to the black hole, where the h by r increases up to 0.1 or so. And the magnetic structure we set by following Jani et al. And the vector potential by setting up vector potential Fi. That's where M is very interesting parameter. With lower value of M, field lines are more inclined towards the equatorial plane of the disk, and the poloidal component is stronger. And whereas if M is higher, then the field lines are more vertical and the poloidal component is weaker. So that means by tuning M, we can fuse more flux around the equatorial plane or around the accretion disk, more magnetic flux. And so in order to understand the physical nature of our initial setup, we evolve our setup by putting magnetic field to be 0. In our simulation, we do not have any explicit viscous heating or radiative cooling. In fact, it is in ideal limit. But due to the local heat balance condition in thin disks, the combined effect of cooling and explicit viscous heating is negligible. So we found that after sufficient simulation time also, our setup remained thin. So this makes our setup suitable to study the effect of magnetic field in the dynamical properties of accretion disks and corresponding jet launching or disk wind driving event in ideal GRMSD limit. In the movie, we saw the temporal evolution of logarithmic normalized density profile in the poloidal plane, where with the prescribed magnetic field. So with time, the accretion disk evolve and it reaches a quasi-steady structure, and we can divide this accretion ejection system into 3 major parts. This is the low density funnel region around the rotation axis of the black hole. Then we have the disk swing region occupying the off equatorial part of the disk. Then we have the thin accretion disk around the equatorial plane. And after certain simulation time, if you notice the region around the event horizon, we found that the disks truncate from the event horizon and start to do oscillation. And by looking at the vertical velocity and the colloidal magnetic field lines, by looking closely around the event horizon, we observe that the field lines are routed to the ergosphere, and that is a typical signature of active plane function mechanism. Also, in the funnel region, the Lorentz factor is as high as 10. And superalbanic, of course, as I like the maximum value of Lorentz factor is also depend on the flow density model, and it is the magnetization is greater than 1, and it is gravitationally unbound. So which like confirms the presence of active plane function mechanism. On the other hand, in the disk wind region, the disk wind leave the surface of the accretion disk with superalbanic velocities with B tor by BP, that is the ratio of toroidal component to the poloidal component of the magnetic field, very high, very near to the black hole, and that is that is a signature of B tor dominated disk wind, and that is turbulent in nature. Whereas far from the black hole, we see that the disk wind leave the surface of the accretion disk with subalbanic velocities, and it becomes superalbanic when it moves far from the equatorial plane. And the B tor by BP is also close to unity around the equatorial plane. And this fact strongly suggests the presence of active plane for plane mechanism or the magnetocentrifugal acceleration in our simulation. And we observed that the velocity of the disk wind of the order of 0.1 to 0.2 c, that is speed of light. Here we saw the inner structure of our accretion disk, and here we plot the toroidal component of the magnetic field with the field lines, and we see that due to the turbulent amplification of the toroidal component of the magnetic field, it changes its polarity in some places, and it drives reconnection in the field lines. And the source of turbulence is mostly magnetorotational instability in the weak magnetic field region, and in the strong magnetic field region, it's most probably magnetic Rayleigh-Taylor instability, and as suggested by many other authors earlier. This reconnection leads to formation of plasmoids. The plasmoids has tremendous application in astrophysics, as explained by my previous speaker, that this kind of plasmoid can can help us to understand the non-thermal radiations from astrophysical sources. Here we have plot the temperature around the black hole, which is like which we can obtain by the ratio of P by rho. So we observe that in the beta dominated turbulent disk twin region, where we observe plasmoid, the temperature is higher than the other region of the disk. So that means it acts as a hot disk twin corona around the black hole, and such corona can have tremendous application. And also it is crucial to maintain the large scale structure of the Blandford-Janai jet. Many suggest that this region play crucial role in collimation of the jet as well. Also, in the first day, as suggested by Nikos Tyflis, that this region is very important to understand the correlation between the time lag and power law index of black hole X-ray binaries. Here we study the accretion rate and mass flux to the funnel region, disk swing rate, for our different simulation model by varying magnetic field strength and the inclination angle of the field line. The consequence of oscillation in the inner part can be clearly seen in the accretion rate. We found that with the strong magnetic field and inclined magnetic field, so strong accretion, and that means the accretion process is magnetically driven, and accretion rate is strongly correlated with the initial magnetic field. And we find that the oscillation feature is more prominent with lower value of plasma beta, that means strong magnetic field, and lower value of M, that is more inclined field. Also, we observed that the normalized magnetic flux accumulated around the horizon reaches above 10 from some of our models and so they achieve MAD, or magnetically arrested disk. For magnetically arrested disk, this typical value for my current setup will be around 15 or so. So then this kind of MAD models are particularly important to understand the recent observation from Event Horizon Telescope. Finally, our findings can be summarized with a schematic toy model of accretion ejection system, where we have Blandford-Janai jet around the rotation axis of the black hole. Then we have the Tor dominated disk winds, which is turbulent, and we observe plasmoids in this region, and which also act as a disk wind corona around the black hole, and that is very crucial to determine the properties of even the Blandford-Janai jet as well. Then we have Blandford-Payne disk wind, which is more prominent with stronger and more inclined field lines. And of course, the oscillation in the inner part of the accretion disk can be related to the flaring activities, and which required more rigorous study for real life application with all emission maps and everything. And also, I would like to note that our toy model is in agreement with the polarized image of M87 as observed by the EAST collaboration that predicted the presence of dynamically important and mostly poloidal magnetic field lines around the black hole. And thanks for your attention. I will be very happy to answer if there's any queries. And this I just translated in Google, so I really do not know how to read, but thanks a lot again for the organizers for giving me this opportunity to present. Thanks a lot.
And thank you, Indu, for being on time. And that's a very good translation indeed. I see Andonis has a question.
Hi, Indu. This is Andonis. Thank you for the very interesting talk and presentation. So I would like to ask you, have you checked how much mass is left in your disk? Because it seems that you have an enormous amount of matter ejected from the disk wind.
Right, you are correct. That is, and indeed, we thought about it, that how it is happening. And actually, we lose lots of mass through the disk wind, but as we are not continuing our runs up to very long times, and that's why we did not care much about that aspect. And in fact, this oscillating feature that we see when most of the means it lose significant amount of mass from the disk. So yeah, and that we have not actually calculated exactly how much amount of mass left in the disk.
Thank you.
And yeah, thanks Nathaniel, because your paper helped me a lot to do this calculation.
Thank you both. I see Nectarius has a question.
Yeah, thank you, Indu. Nice work. I would like to ask, what is the Lorentz factor and the plasma beta in the diskwin part?
In the diskwin part, plasma beta is always like greater than 1, less than 1. That means it is magnetically dominated. But in the disk region, if okay, let's say in this region, if you see in this region, it is always like greater than 1. This region is always gas pressure dominated, and this above the diskwin is always like magnetic pressure dominated.
So the ratio is about what? I mean, 0.1, 10 to the minus 2?
Oh yeah, it certainly drops up to like after when at the disk surface, that means where the density falls drastically, it goes like 0.01 or 10 to the minus 2 or so.
Okay, and the Lorentz factor, what is the Lorentz factor at the high 40, let's say, that we show here?
Oh, in the diskwin region, right?
Yeah.
Diskwin region, Lorentz factor is pretty low. It is, if you consider the velocity to be 0.1 to 0.2 c, it will be, I think, around 1.25 or even less.
Okay, thank you very much.
Thanks a lot.